Herzlich willkommen zu einer neuen Folge von Startup DNA. Heute mit einem Portfoliounternehmen von 10x DNA. Deswegen ist Richard dabei. Vielen Dank, dass du Zeit findest. Es geht um Li-Cycle, ein kanadisches Unternehmen, das Batterien sehr energieeffizient recycelt, also die ganzen Materialien wiederverwendbar macht. Ein ganz wichtiges Thema. Wie gesagt, das Unternehmen sitzt in Kanada, deswegen sprechen wir Englisch mit dem Team, aber trotzdem ganz viel Spaß dabei. So today we have quite an interesting talk with an investment from 10x DNA. Richard from 10x DNA is with me, but we have a very important guest. So over to you. What's your name and what you're doing?
Hi, my name's Tim Johnston, and I'm the executive chairman and one of the co-founders here at Li-Cycle. At Li-Cycle, we recycle lithium-ion batteries from all different formats, and really looking forward to talking to you today a bit more about what we're doing and what we're planning to do going forward.
Great. So for us, Li-Cycle, a very interesting investment because we need to come to a future where we also recycle batteries, and we will dive into this later. But first of all, we also always care about the entrepreneurs behind the company. What's the story? What's the vision? And maybe you can take us through your kind of first days. Like how did you start the company? What was the magic moment? So how did everything start?
Yeah, absolutely. So my background is I'm a mechanical engineer and CFA charter holder. And I was very fortunate that in the mid to late 2000s, I got involved in the lithium-ion battery industry. First on the battery side, we were developing a project for a company actually in China back in about 2008, 2009, looking to produce lithium-ion batteries. That led into a lithium-ion battery chemical project being lithium carbonate in that time. And we built as the company the very first fully continuous lithium carbonate processing plant in China. And on the back of that, really got quite aware that this wasn't just a one-off problem. This was going to be something that was going to be critically important around the world, and was able to build a specialty practice within the firm focused on developing lithium projects. And so for almost the next 10 years, I had the pleasure of helping companies all over the world. So when we talk about primary lithium, we're talking about, from brines, clays, hard rock material, from Australia to South America, Europe, North America. I was helping these clients work out how to scope out, how to develop, and now ultimately how to build and finance these projects, which is also where the CFA part came in. And so you can sort of see that was really the prelude to Li-Cycle was from the mining industry. And periodically we would get these questions as to, well, what happens to the batteries at the end of their life? And to be frank, after being asked this question multiple times over a number of years and still not being able to give a good answer, in 2016, I left the engineering firm that I was with my fellow co-founder, RJ Kocher, who's our CEO, and we started Li-Cycle because we really believed that, A, there was going to be a need, that the whole reason why the lithium industry was being built out was to support sustainability, to green our grid, to reduce the amount of carbon that we're producing globally. But you couldn't do that if you didn't have a sustainable recycling solution. And when we looked at what was out there, basically the world was treating lithium-ion batteries like a hazardous waste, burning off the organics and the plastics and creating a huge amount of emissions in the process. And then at the end of all that, the material going to a smelter where they couldn't recover the lithium anyway. And so coming from the lithium world, that was almost sacrilege in the sense that we put in all this work to pull these materials up out of the ground, put them into batteries, and then weren't actually able to capture them at the end of that battery life, despite there still being a lot of useful life in those materials for future applications.
Yeah, great. I mean, you mentioned that this is going to be one of the core questions of how we can basically achieve the energy transition. Maybe to get started, could you walk us through what is actually contained in a lithium battery, lithium-ion battery. So which materials, how are they typically mined, where are they mined, so that we get an idea of what we're actually talking about here.
Yeah, not a problem. So when we're talking about lithium-ion battery, you can really think about it in two main components: the anode, which is copper and graphite, and then the cathode, which is aluminum, which is the current collector, and then all of your critical battery materials, so nickel, cobalt, manganese, lithium, they all exist on the cathode side of the battery. So when we look at the traditional sources of these, of course, things like copper and aluminum, they're widely utilized throughout society in a whole range of different applications. They've been mined for a long time. So I'd say they're very stable, commoditized inputs for the lithium-ion battery value chain. Where the development has really come from lithium-ion batteries is in the specialty materials component. So on the anode side, you have graphite, and the graphite, it's not just coal that we've pulled up out of the ground. I mean, it's all carbon based, but the form factor of the graphite is really important. And today, the graphite is mined. A lot of it comes from Africa. There's mines in North America and in Asia as well. And so that is a relatively large and growing industry in order to support the anode side. Where a lot of the work and development has been and will continue to need to be done is on the cathode side. And so if we're thinking about nickel, the number one use for nickel in the world today is for stainless steel. And but the form in which it goes into stainless steel is very different to the form in which it needs to go into a battery. So when we're thinking about these metals, it's important to consider them not just as commoditized metals, but really what is the form factor? And I'll use a very simple example on the nickel side. So traditionally, most of the world's nickel was produced in the form of what we call nickel pig iron, which is effectively an impure form of nickel. It contains a lot of iron, but of course, because it's going into stainless steel, that's totally fine. For lithium-ion batteries, what we're looking for is the isolated nickel in a salt form, typically in a sulfate, that then is converted into a hydroxide in pCAM, and then ultimately into cathode. That specialty form of nickel requires significantly more refining than the traditional nickel pig iron. However, the traditional sources remain. Nickel is predominantly produced out of Indonesia, being a major supplier. Russia historically was a major producer of nickel. And then, of course, we produce nickel here in North America and in Canada, as well as in Australia.
What about Europe?
Europe, there is some, but very little. Most of it was actually coming from what I would call Eastern Europe. And so with Norilsk out of Russia, that's where most of the nickel was being mined. Now, there is refining that takes place. So, for example, there is a facility in Norway that's owned by Glencore in Kristiansand, where they actually take nickel that is mined predominantly in North America, converted into an intermediate material at their smelter in Ontario, and then taken to Norway to be refined into individual cathode metals, including nickel, cobalt, and copper. So that's generally where the nickel is produced. Cobalt, 70% of the world's cobalt still comes from the DRC in Africa, and that material is exported mostly as an intermediate material, what we call cobalt hydroxide, for example, where it's sent predominantly to Asia, where it's refined into a whole range of different end products. The main end products being cobalt metal, which is used in the alloying industry, and cobalt sulfate, which is what's required for the battery industry. And the battery industry is a major demand use for cobalt. The key thing about cobalt to understand is that it is a byproduct. So the mines that produce cobalt today generally are not mining cobalt as the primary material. They're mining it as a secondary material. Out of the DRC, the main target is actually copper, and they actually get the cobalt with the copper. And so that's why we see a lot of variability in the pricing and supply historically of cobalt as well, because nobody was developing it purely for the cobalt. It was always driven by the copper. Of course, manganese, the predominant use in the world today for manganese is steel. And anything that is steel, or, a derivative of steel, is an enormous market. If you look at the volume of steel that we produce globally, it's orders of magnitude greater than anything else that we produce as a metal today. And so manganese is a very widely produced material. But once again, it's the form factor. So manganese sulfate is predominantly refined and produced in China for the battery industry.
Mm-hmm. And what about the lithium side?
I was going to get, so my favorite one, right? So lithium. Lithium is a really interesting commodity, and that's because it's not really a commodity. It's very much a specialty material. Most of the world's lithium today is produced in two places. Australia. So Australia produces what we call a hard rock concentrate. So this is what you would typically see open cut mines producing a concentrate. Until recently, that concentrate was then going to China, very similar to the very first project that I was talking to you about, to be converted into chemicals, lithium carbonate or lithium hydroxide, for the battery industry. The second major area where we produce lithium from is from what we call the lithium triangle, which is essentially Bolivia, Chile, and Argentina. Whilst we don't produce any commercial volumes from Bolivia, most of the world's lithium from this region comes from Chile and Argentina, with both SQM and Albemarle being major producers on the Chilean side, and groups like Alchem, which are on the Argentinian side, producing lithium carbonate.
Mm-hmm. So now that we talked about where these materials come from, can you give us an idea about the environmental and social impacts that the mining of these materials has, and why you think, or is this a problem? How big a problem is it, and why do we need to tackle it?
Yeah, absolutely. And so I think the two key ones that have had historic question marks around sustainability impacts is really cobalt and lithium. And cobalt, because cobalt is produced in the DRC, and companies like Glencore, who we partner with, are doing really good work for responsible sourcing and mining of cobalt. Traditionally, cobalt has been associated with things like child mining and other social issues around that. I would say the industry has improved its standards overall in terms of trying to make sure that we know where the cobalt is coming from. But of course, it still happens in the DRC, and there is groups that will take advantage of that, but happy to say that's becoming the minority. So things are getting better on that side. When it comes to mining lithium, of course, any mining project has some level of environmental and social impact. And as a result of that, if we look in Australia, we're talking about big open cut mines, significant amounts of tailings or waste material that is generated and has to be stockpiled on site as part of these operations. But when we come across to South America, and we're talking about the lithium triangle, one of the biggest challenges of producing lithium in this part of the world is the need for fresh water. So where do you find lithium in these areas is in some of the driest places on Earth. So the Atacama, the Salar there, where Albemarle and SQM produce lithium from, is known as one of the driest places on Earth, but you need fresh water. So there's always this balance about how much fresh water can you pull out in order to process the materials, in order to get to the lithium chemicals that you want. And that's the balance, and that tug of war has been going on for years and will continue, to be frank. I don't think it's not like the Atacama is all of a sudden going to become plentiful with water. It is going to continue to be a balance. They're, of course, making good strides to improve their processes to minimize water, but it will remain to be attention.
Okay, understood. And now when we move a little more towards the batteries, how does the typical life cycle of a battery look like, or basically the materials within the batteries? Can you talk us through this and how they are typically, what happens to them at the end of their life today? Are they recycled? Which fraction is recycled? Can you give us some color there?
Yeah, absolutely. And so when we mine all these materials, the first thing we have to do is get them into a form which we can use them in a battery. And that typically goes through a couple of processes. So we take these sulfates or these salts, these specialty materials, we convert them into a precursor material, which we call PCAM. And then we convert the PCAM with lithium into the cathode active material, which is one of the key components. Now, as we step into the manufacturing process, what happens is we're combining all the components and we're going through a relatively complex manufacturing process. If as you look at the details of a lithium-ion battery, there's a lot of individual components. There's a lot of work that has to happen from those raw material inputs to the finished product that you see. And so we actually see quite a lot of scrap come out of this industry. Long term, we're forecasting something between 5 and 10% of all critical materials that go into the lithium ion battery system will actually come out as scrap before they actually ever end up in a useful product. So, if you think about the world's global demand for critical materials in the battery world, and you take 10% of that, and you say, well, 10% of that is coming out. It's just waste off the top. That's a perfect feedstock for recycling. And I would say one of the things that the cell manufacturers have gotten good at over recent years is actually being able to identify value for this, identify quality partners like Li-Cycle to be able to take that material and then reproduce it back into fresh materials that can go back into their supply chain. So it's not like they're losing that full 10%, but in fact, they can actually get it back. Now, as we step through the life cycle of the lithium ion battery, there's really a couple of things that happen. One is there is, of course, such things as premature failures. Like any complex system, occasionally there's going to be quality control constraints that mean that something fails before it was meant to in terms of its design life. So this, for example, we work with a number of large automotive companies and their dealer networks. So if you're driving an electric vehicle and something goes wrong with your battery, it's not charging properly, there's something wrong, you take it back to the dealer, they fix it. That may mean replacing part of the battery, it may be replacing the whole battery, and then we'll ultimately get that material back. I would say the industry does a very good job of making sure that that material comes back to recycling because it's easy for them to capture. The hardest material to capture is ultimately the end of life material. And what do we mean by end of life? We mean that, okay, so once the battery is done or you're finished with the device, what happens to that? And you really have to look at it segment by segment. And starting with consumer electronics. So if you think about things like cell phones, tablets, and the like, that is traditionally that was the largest sector of lithium ion batteries. Now today it's much smaller than the electric vehicle market, but it was also the hardest material to capture. So where in Europe, we were typically capturing over 50% of this material to come back for recycling. In North America, until recently, that number was as low as 5%. So we had a lot of that material going to landfills and going to general waste. I'm happy to say that that number is now creeping up. But what's happened, obviously, is the other sectors have now dwarfed it in terms of size and scope when it comes to recycling. The second sector is energy storage. So we think about grid storage, think about backup power. These systems are relatively large, but they're discrete. And so you might have a system that has several hundred tons of lithium ion batteries in that system, and it needs to be retooled periodically. And depending on how hard the system's being run, that system may need to be retooled every 4 to 7 years. And that contractor will have the responsibility of making sure that those lithium ion batteries are recycled. So once again, that sector, we have very good visibility and we're able to capture that material quite well because they're large, discrete volumes managed by professional contractors.
Mm-hmm.
The final sector, of course, is electric vehicles. Now, we talked about the manufacturing side of it, but when it comes to end of life, we're really in the early stages of end of life. And what we're seeing is that this material is going to be a significant portion of our future feed. So when we look at the back half of the decade, we see the end of life material from electric vehicles is going to be a key driver in terms of growth. And the benefit of electric vehicles is similar to energy storage. They're large, discrete units, and they have value. So the end of life auto recyclers, the traditional groups that take automobiles and scrap them, they're after the steel, the aluminum, the copper, but now they have a battery, and that battery we can provide value for. So there's an incentive for them to go and get it and then return it back to recycling. And so I would say in the early days, we did see some stockpiling because, to be frank, groups were just not sure what to do with the material. They would get these cars in their yards, they'd pull the battery out, and then they're like, okay, I'm not sure what to do with it. I definitely don't want to pay to dispose of it because that's not their model. They're like, and so they would sit on it. And so now we're starting to see some of those volumes come out. But as we're working with these groups and we're educating them about the value that we can offer for this end of life material, we feel very confident in the future that we'll also be able to have really good visibility and capturing of that. Now, of course, that's what I'd consider the bottom net. There is one net that sort of sits slightly higher than that one when it comes to electric vehicles, and that's of course through the OEMs themselves. And so one of the things that we're seeing is an increased desire for the automotive companies to get that material back. Of course, we all know that things like lithium are in critical short supply. So if they can secure those units and get them back through recycling, it actually helps them benefit from additional supply of these critical materials. And so what we're seeing is increased number of business models that OEMs are running, whether or not it's through leaseback programs or similar, to try and capture that material as well. But this is only going to add to our ability to be able to get this material back and ultimately bring it in for recycling.
Looking at Li-Cycle, it's a very, very important mission. But when you look at scaling your business, what are the challenges? Is it like the feeding, so that you say we could scale the hubs and the recycling process basically limitless, or do you say that's a problem to scale it? When you look at the management, what are your worries about the business? What are the bottlenecks?
Yeah, absolutely. I mean, the big thing is, and it comes back to how we even designed Li-Cycle. If I'm talking about pre-processing, so what we would call a spoke operation, where we receive all these battery materials and then we convert them through to intermediate high value products, is one of the biggest costs has always been the logistics. So if you have a battery on the other side of the country that needs recycling and your recycling facility is 5,000 kilometers away, well, then all of a sudden you have a very big cost of recycling to get that. What we're doing, and this is, I guess, one of the key things that we're continue to be focused on, is building out this network of spoke facilities. So the idea is that with a network, this decentralized approach, we can be close to where battery materials are being generated to make sure that we can actually get them. Because coming back to the end of life auto recyclers, for example, they don't want to get rid of these batteries if it's going to cost them to get rid of them. And so if we can reduce that logistics cost, we can increase the overall benefit that we can provide to getting them. So I'd say that's definitely one part of it. The other bottleneck that we see coming forward is really on the refining side. So, in terms of barriers to entry, to build a pre-processing facility, you're talking about it's a smaller facility, lower capex. There is relatively rudimentary ways that people are doing this and have been doing this, some better than others. But in essence, that is a way to get the materials. But the refining capacity is not such a simple task. At the end of the day, you're talking about a much bigger capital investment. You're talking about significantly different skill set to be able to run a hydromet facility like ours here in Rochester. And what we're seeing is that there's actually not going to be enough refining capacity coming to the market going forward. And so we see facilities like Rochester, everyone always wants to know, well, how do you see filling up the capacity of the plant? I actually look a bit at the other way and it's like, well, how do I make sure that I can continue to service my customers by making sure we have enough refining capacity in our network? Because whether or not it's with Li-Cycle or with others, we're just not seeing enough refining capacity come to market today.
Mm-hmm. And if we So you mentioned your spoke and hub facilities. Maybe I think it would be interesting for our listeners to actually understand the actual process. So what do you do step by step from getting a battery that is end of life or scrap to selling the actual materials back into the market? Can you walk us through this process, please?
Yeah, absolutely. So we have a two-part business model and technology, and we call it the spoke and hub model. And essentially, what our spoke facilities do is we receive all different formats of lithium-ion batteries. So if you go to one of our facilities today, you can see full electric vehicle battery packs being run alongside manufacturing scrap or cell phone batteries. It can all go through the same front end of the plant. And that's really important because in the early days, what we wanted to make sure is that we had as wide a possible funnel. How do you reduce costs and build in efficiencies into your business? One of the ways is through scale. And in the early days of building out this industry, having that broad aperture and that broad capability has enabled us to build scale, which is an important factor. So what do we do? So we take the materials in. We have our own IP protected process, which we call submerged shredding. And basically what that means is that we can take batteries in, we don't have to discharge them, and we don't have to dismantle them. Today, we're the only facility in the world that can process an entire electric vehicle battery pack, which may weigh up to 700-800 kilograms in a single pass. We don't touch it. It literally loads onto the conveyor. It'll go up into the plant. It goes through our first shredder. And what we're doing in the first stage is really, really important. So the whole system is submerged in a water-based solution that's really doing three things. The first is that the solution allows us to prevent the possibility for fire. So of course, without any free oxygen, we're not exposed to the atmosphere when we're breaking them up. We can actually prevent the fire from propagating. The second part is because these batteries contain energy, the solution can then take the energy away from the system. It can actually pull that energy away. It comes out in the form of heat, and we can keep everything nice and cool. And then the third part of it is that we're actually able to chemically treat the electrolyte. So one of the things we didn't touch on earlier is the electrolyte within the lithium-ion battery. It does have some potential nasty components, and what we're able to do is treat that chemically to lock up those components as we're breaking up the battery. So now the battery is going through the plant, and essentially what we're doing is we're taking that battery or those battery materials and we're breaking them up into three key products. We produce a low density plastic, which is mostly the plastic from within the lithium-ion battery. The second component that we're producing is what we call our metallic shred. So this is like the things like the copper and aluminum that I was talking about as the current collectors within the battery, but it's also the casing materials, the aluminum packaging, etc. And we produce that as a shred product. And then the key thing that we're after is what we call black mass. Now, black mass is just the industry term for those anode and cathode materials. So the graphite, the nickel, the cobalt, the manganese, the lithium, they all reside within this product as black mass. Now, one of the benefits of what we've done is we've taken something that is somewhat difficult to handle, because lithium-ion batteries have their inherent dangers associated with handling them. And we've converted them into high-value intermediate products that are safe and easy to transport. We can then sell the plastics and the shredded metal into the local markets. And now, instead of moving the full weight and volume of a lithium-ion battery long distances, we're now just focused on moving the black mass to our refining facility, which is what we call the hub. Today, we sell black mass. And so the same groups that we were looking at, well over 10 years ago when we're looking at what is going on in the industry, that material, they can still recover the nickel and cobalt. Unfortunately, they don't recover the lithium. But that's been a way for us to step into the business to be able to support our customers whilst we build out our own refinery, our own hub. So today we're building a hydrometallurgical facility here in Rochester, New York. Once complete, we'll be able to process 35,000 tons per year of black mass. To give you an idea, that's about 200,000 electric vehicle battery packs of material that we'll be able to process here per year. And from this facility, we're going back to those critical materials that we were talking about: lithium carbonate, nickel sulfate, cobalt sulfate. and we're actually able to sell them back to the same customers that we were able to get the materials from in the first place. When finished, it'll be one of the largest facilities of its kind in the world. It'll definitely be the largest in the Western world. And what that scale does is it means that we can actually be a meaningful provider of these critical materials to our customers.
Okay. And this process that you employ on the hub side is a hydrometallurgical process. Can you first of all explain to us what a hydrometallurgical process is and how this compares to what the industry is doing normally, or what your competitors may be doing?
Yeah, for sure. So traditionally, people would take the materials and they put it into a smelter, and a smelter effectively is a furnace. It gets very, very hot. You're talking about over 1400 degrees Celsius, and they'll melt everything down into an alloy, a metal material. The challenge with that is that the lithium is a very light metal, and so it ends up going up with the off gas or going to what we call the slag, which is the waste component. Of course, the graphite's burnt off, any aluminum's burnt off, etc. And so now they've really just got this mixed metal of nickel, cobalt, and copper. They then take that and they go through their own hydrometallurgical process at that point by taking that intermediate material and then doing what they call a leach. So a leaching process is effectively where you add acid in a water-based solution to dissolve those metals into solution so that you can then go through purification and separation. And that's what they do in that process. The difference for what we do is we take that black mass material and we go directly to the hydrometallurgical process. One of the things that we could never quite understand, and it was simply because these were legacy assets that were never built for black mass, was that if this was a material in the Earth's crust today, these metals are all what we consider highly soluble in an acid solution. So we take that black mass in and we can dissolve all the metals into solution at the front end of the process. We don't have to melt them down and produce this alloy first. And the benefit of that is, of course, you have significantly lower emissions, but you also have significantly lower energy demand because that material is effectively not having to be heated up to those extreme temperatures to melt everything down. And the key thing from a value perspective is the lithium is still there. So lithium is one of the materials that then gets dissolved into this solution. We then go through 2 stages of purification. So the first stage is we're removing the copper. And so basically we're able to precipitate out the copper and produce a copper-based product that we can then sell on for further refining. We then remove any iron or aluminum before going into the heart of the plant, which is where we actually start to separate out the metals. And so we use a process called solvent extraction. One of the key things about the hub design is that whilst our process is patented, the flow sheet itself is unique. What we've done is essentially borrowed unit operations that have been done in the mining industry for a long time. They're well developed, well understood, highly efficient processes. Solvent extraction is one of those processes. And what we can do is we can selectively remove the manganese, then we can selectively remove the cobalt, and then the nickel. And then once we've isolated those metals, we can produce the different end products. So in the case of manganese, we produce manganese carbonate. For the nickel and cobalt, we produce sulfate crystalline product. At the back end of the plant, that's now we basically recovering the lithium. And so we're able to go through a very similar process to what we use in the lithium industry and take that lithium in solution to precipitate a lithium carbonate. We then refine it through a bicarbonation process, also used in the mining industry, to ultimately end up with a battery-grade lithium carbonate product. So you can see, relatively linear process where it's effectively going through and selecting off the different metals, but all using standard operating principles that we've used before.
And how much of the material can you actually recover with this method? And second question, what is the challenge bringing this from a lab scale to a large industrial scale for you?
Yeah, great questions. And so, we can recover up to 95% of the materials. Now, what we look at is we look at it from perspective of a couple of different perspectives. One is RER. So RER is recycling efficiency rate, which is a common term that is used around the world today. And effectively, what we want to make sure is that the metals coming in are going out in a product. And one of the things that you didn't hear me talk about when we talked about our process were waste streams. When we talk about our spoke facility, we have zero liquid discharge. We don't produce any effluent waste at all, and we only produce those three key products. So there's no tailings, there's no big landfill associated with that. We then go on to the refining process, and because we're individually producing those different components, the same thing. So you come to our site, there is no tailings facility. There's only products that we're producing from the facility. And so that's how we sort of look at it. The challenges associated with getting it from a lab scale to a commercial scale are significant. Essentially, what we've had to do is we had to refine the process in the lab in order to be able to understand the chemistry. We then built a demonstration plant, and we spent $10 million, and we operated for nearly a year a demonstration plant in Canada, taking black mass that we produce through our spoke facilities and then converting it into those same battery chemicals that we were talking about before. And as part of that, what we did is we reviewed the scale up, because always the question is, okay, so what is the scale up that you're going from a demonstration facility to a commercial facility? As I said, we're going to process 35,000 tons per year of black mass. One of the benefits of utilizing existing unit operations that have been proven before is there's actually very good metrics for scaling the chemistry. The equipment's been done before. We're not the first ones to build a solvent extraction plant. We won't be the last ones to build a solvent extraction plant. But the chemistry scaling factors are important. And so that's what we were able to match all the way through. And so we did that work. On the spoke side, we went through a very similar process, but of course, we're operating that commercially today. And so very much, the focus is on the hub. And we feel like we're in a really good position to not just finish off the construction, but to ramp the facility up successfully.
What is the timeline here currently?
Yeah, so we're targeting starting commissioning in late 2023. So commissioning will happen in stages as we basically complete different circuits and start to ramp up thereafter.
All right. And let's imagine this all works well. How fast can you scale then? Because we will have a lot of batteries, so the feed is not a problem. We will hopefully switch very fast to EVs, so we'll have a lot of capacity for you. So what's then your challenge in building many of these facilities?
Yeah, on the spoke side, we've been able to refine the process down. One of the things that we said, okay, if we're going to build lots of these, and the intent is obviously to build lots of these eventually, is that we have to come up with a standard design. And the benefit of processing lithium-ion battery materials is that the materials we process in North America are the same materials that we process in Europe. And so having this standard design, we're actually able to build the facilities. So we actually have our own construction facility in Canada where we build the modules, we pre-test them, and then we send them to site. So we can deploy a spoke facility, depending on permitting, anywhere between 6 and 12 months to execute on a single site. But we can also run multiple in parallel. We've just completed Arizona and Alabama here in the United States over the last few months, and we ran those projects concurrently. So we've been able to demonstrate that we can build out our spoke facilities very quickly. When it comes to the hub facility, these are long lead projects. At the end of the day, we're talking about, by the time we're done here, it'll be, about 18 months of construction that we've put into building the facility here in North America. So it comes back to that premise of, as we look to the future, making sure we understand what are our customers' needs on the refining side, and then planning sufficiently ahead so that we can actually meet that in the future. Today, our focus is very much on the completion of the Rochester hub, and getting that done and getting it built well is very, very important. To build a bigger facility from there, it's not a stretch. At the end of the day, you're talking about the same unit operations. We're at the small end of the scale in terms of what's used in the mining industry. So there's lots of room for potential expansion on the processing side.
This year, and I think also last year, you announced a couple of collaborations or partnerships with either battery manufacturers or mining materials companies. Can you tell us about these partnerships? And so what is the content of this partnership, and why do you think this is necessary to actually make your business successful?
Yeah, absolutely. And so, one of those partnerships was with LG, and the other one was with Glencore. Both have selected Li-Cycle as being their preferred recycling partner. LG in North America, and Glencore, we have a global partnership that we're working with them. The reason why we saw these as good fits is, if I talk about LG, LG today is one of the largest manufacturers of electric vehicle batteries in the world. And they have a growing footprint of facilities that they're building out around the world, both in North America and in Europe. And so for us, the benefit of working with a group like LG is that not only will they generate a lot of materials as part of the manufacturing process, but they also have a high demand for the materials to go back into their supply chain. So us being able to close that loop for them, we saw as being a really strategic partnership as they continue to build out their assets around the world. On the Glencore side, Glencore today is one of the largest producers in the world of nickel and cobalt, two of the three critical materials that we consider in the lithium-ion battery value chain. And so when we're talking to customers and they have a need for material, having a partnership with a group like Glencore enables us to be able to provide a better offering. Collectively, Glencore can provide both primary material and with Li-Cycle secondary or recycled material to support their overall supply or demand needs. The other benefit is that Glencore is a large operating company. I mean, they are a significant recycler themselves in the e-waste world. So they take a lot of e-waste scrap and process that through to copper products and other intermediate products. And so there's a number of areas where their experience will benefit us, our experience is benefiting them, and we continue to see this being a great partnership as we build out assets.
Mm-hmm. Now, these two companies are obviously interested in the valuable materials within a battery. Now, one thing that we see when we look at the industry in general is that people try to find battery chemistries that contain less of these valuable materials, such as cobalt and nickel. Or maybe even in the future not use even lithium anymore and instead use sodium or something like that. Are you worried about this trend? So is recycling really going to be needed in 10 years from now still? Or how do you think about this?
Yeah, absolutely. I mean, it's interesting. So I'll talk about lithium-ion chemistries, and then I'll talk about potential for future chemistries as well. But when we look at lithium-ion chemistries, today the most valuable component of any lithium-ion battery is the lithium. When we started Li-Cycle, we used to say that it was roughly, the value was broken down by basically a third lithium, a third nickel, and a third cobalt. Today, it's something like 2/3 to 3/4 lithium, and then the balance is nickel and cobalt. As an industry, we've pushed down that content in terms of cobalt content and moved it to nickel. And at the same time, the lithium value has increased significantly, which has sort of moved that around. So regardless of whether it's LFP material, for example, lithium iron phosphate, which has no nickel and cobalt in it, or if it's NMC 811, which is nickel, cobalt, manganese bearing, we still see that one of the greatest value creators that we can do is recover the lithium. And we can do that across the full spectrum of lithium-ion battery chemistries. So we don't see the demand for recycling in the lithium-ion world going away. In terms of next generation batteries, we're continuously looking at this. This is always part of our R&D roadmap in terms of what's coming down the pipeline. We're very strong believers that lithium ion is here to stay for the foreseeable future. We'll continue to get better. That next generation batteries will look to improve upon what's been done on the lithium ion space with things like solid state, for example, which for us is great because when you look at the overall lithium intensity in the battery, you're looking at an increase there, which just means you've got more value to ultimately recover going forward. And as other chemistries evolve, we'll be able to utilize our experience, our diverse network and footprint of assets in order to be able to service whatever comes to the industry.
So there is a great future ahead, and we also believe that there's always enough to recycle and enough need. But the question is, how will you fund this? We having a background from startup investing, it's always a challenge how to get the right funding. So what's your view, your plan on how to fund this?
Yeah, so to date, Li-Cycle, we've raised over $1 billion in capital. And so we're well funded to this point for all the capital projects that I've talked about today that'll build out 7 spokes in our refinery, our hub here in Rochester, New York. So we consider ourselves well capitalized for the needs of the business today. As we continue to look forward in terms of future opportunities for growth, one of the things that we're seeing is increased support from things like government financing and industry financing in order to support future growth. But I would say for today, we're well financed. We're in a very good position when it comes to the capital needs of the business. And we'll look for opportunities as we continue to grow the business as required.
Can you also comment on the current status of the regulation, both in the US as well as in Europe? Do you think additional changes are needed in terms of the mandatory recovery rates or something like that? How do you view this topic?
Yeah, absolutely. So it's interesting. What we're seeing is actually almost 2 parallel paths being developed in the industry. So from the North American perspective, we see that the market will continue to be very much an open market. And we've seen things like the IRA bill come in to support and encourage people to invest and build assets in North America. And to date, this is working very well. We've actually seen capital being deployed. We've seen companies coming and committing to building assets here in North America. When it comes to targets around this, how they're continuing to build this out is less so in terms of targets of recoveries, and we'll talk about Europe because Europe is different in that perspective, but more about where the supply is coming from. And so that need to localize supply chains in North America, or at a very minimum with OECD countries, is actually what's driving a lot of this value that's being delivered to the industry in terms of financing. You compare that to Europe. Europe is going a different track. Europe is actually progressing much more towards what we would consider a closed economy. We're seeing increased guidance on recycling efficiency rate targets. So for example, in Canada, we already have in Ontario a 70% target. So 70% of the materials that we receive today have to go out as products from our facility in order to be qualified as a recycling facility. In Europe, we're seeing that target should hit by the second half of this decade. They're not there at this point, but that's where they're progressing to. But the other thing that we're seeing is that rather than trying to incentivize industry to build, they're enforcing it. So we're seeing increasing regulatory pressure, which what we're expecting to see is that Europe will become a closed economy. So if you want to produce these products, sell these materials, you need to have the assets in Europe. And once the materials are in Europe, it's unlikely that you'll be able to get them out of Europe again, which makes a lot of sense. Europe is not a big producer of critical materials like lithium, nickel, cobalt, like we were talking about before, but they are a big consumer, right, in the nature of the economies that exist in Europe. And so as a result, once they get them, this is only going to drive the need for recycling because ultimately you need them back in a form that they can go back into the industry. And so that's sort of how we see the European landscape being built out over the coming years.
Mm-hmm. And when we now look into the, let's say, long-term future, do you think the world will be able to fully close the loop on battery materials, or like how do you see this playing out?
Yeah, I think it's going to take a long time before we actually end up seeing it fully close out. If we look at the lead acid battery, industry, for example, something like 98% of the world's lead that we consume today comes from a recycled source. I believe that we will ultimately get to that point, but one of the key rationales for recycling today is actually to close the supply-demand gap. So if we look at the demand for these critical materials from industry going forward, we don't have enough primary material coming into the market from the mining industry. And so that's where recycling can help fill that gap. We can help close the gap between what's needed from industry and what the primary industry is going to be able to produce. Now, what I think the secondary effect of that will be is that we'll then see less new primary material coming to the market over time. And as the mines basically reach the end of their life, you'll start to see that decline over the decades to come. And I really look forward to a day when we can say, okay, today we're 98%, just like the lead acid battery industry, from recycled sources. But we have to get the materials first and continue to grow the industry as a whole.
Tim, thanks a lot for finding the time to dive into your company. It's a great mission. We are very happy to be an investor, and we both believe in cradle to cradle. So the end game is that we don't take new materials off the earth, but everything that we took, we recycle. You are on a great path, and looking forward to be part of that journey and see how you progress and grow. And thanks for finding the time today.
Yeah, thank you very much. It was great having you on the show.
Thank you so much, gentlemen. Appreciate it.